Our second speaker will be Matt Ross from the Colorado State University. And Matt will present Tidy and Tedious, Empowering Large-Scale Watershed Science Through Inclusive Welcoming Data Harmonization.
Just need the password. I'll just talk a little while that's getting set up. So thanks so much for having me to this meeting. This is very much outside of my training area. So I'm trained as a watershed biogeochemist. My PhD was at a really deeply local scale. Funnily enough, that's where I first met Miles Reed in like 2015, who's our next speaker, working on mountaintop mining. Oh, not this one. That one's cooler. Yeah. All right, let me get out of there. And then I kind of moved to a larger scale doing some remote sensing. And throughout my work, I was frustrated as a sort of a new scientist at how difficult it was to learn new data sets, especially going from raw data to actual sort of like functional data. And that has become a passion in my career that I'm going to talk about eventually. And so, my lab right now has about 30 to 40% of our work is actually just directly to make data sets where we don't necessarily have a specific research question. We're trying to make these data sets in ways that empower others to look at their own research. And that's where a lot of this experience is from. Basically now close to, I have to like redo this, 8 years or so of trying to publish data and get other people to use it. And that's basically what I'm going to talk about. I'm doing this through the teaching technology that I've started to use during the pandemic, which is the Mentimeter. So there will be some interaction. So be ready to like log in to menti.com. and then put in this code that we'll say at the top of this presentation. You can also scan this QR code. I'm not going to leave it up because you can just go to menti.com. But first, we're going to listen to some birds. I promise I'll try to bring it back for why we're listening to the dawn chorus. Oh, play. Okay. Maybe a little louder. There we go. More birds. Okay, so when I hear this, I actually think a lot about the work my lab does. And what I hear in this bird song is a whole bunch of like different, beautiful, individualized species that are mostly talking to each other, but not talking among species. They're sort of isolated in acoustic space and in space. But I think of the work that my lab does is finding if this sort of natural background song, which in my world is data, can be brought together to sort of form a cohesive picture of what's going on in the landscape. Not with birds, but I like birds. So the first question for the Mentimeter thing is, what did you hear in that bird song yourself? And I can just play it while you fill that out, because you should be able to see the questions even when I'm not there. Do you guys see the question? Head nods? Okay. Okay, I want to just see what you've all said. Love it. Robot drones. Oh, that's a millennial joke. Love it. Maybe Gen Z. So most of it is like we hear birds, we hear chirping, we hear different sort of sounds, trills, etc. I was hoping to see some of these descriptions of these different types of sounds that we hear in this song. And one thing that I don't see is sort of like that it's composed or it's music or it's all coming together. This is sort of the natural background, and I think what I really like is when we can sort of connect these different sounds and make music, and that's what I'm going to sort of try to get to in this talk. Okay, so now no more birds. Now I want to get your opinions on whether you find it easy to work with raw data or if you prefer sort of analysis-ready data or stuff like that. I'll show the responses in a little second. I like for people to answer without seeing them. And I think the scale is 1 to 5, so you can strongly disagree or agree. Okay, so I'm seeing sort of what I maybe expected, which is folks do like pre-harmonized data sets to work with, but maybe there's less consensus that there are plenty of those data sets already available and that they're like relatively easy to access. It does seem like this room, which I would expect, a bunch of modeling, coding types, there's quite a bit of comfort. About half of you seem pretty comfortable analyzing raw data, but still there's some preference towards harmonized data sets. Yeah, this is a fun one. I was excited. So I just asked you to rank your favorite data file types from most favorite to least. I was excited to see this. I knew this would happen. When I do this for my coding classes, NetCDF is always last because we're like ecologists who mostly deal with CSVs. But I assumed among modelers there might be some more preference for some NetCDF. My personal favorite is I prefer direct access from an API wherever I can have that, and I also really like Apache. But CSV is the most inclusive because everybody can use it. It doesn't come with metadata, so it's kind of annoying to work with at the first, but everybody has, any program can use CSVs. So that's not surprising to me that it's shown up there. And I think when we're in the coding space, often we actually go away from CSVs, but they're very powerful if your data is small enough to be used. Okay, so the last one before I really get into my talk, if you had $100 million to invest in our ability to estimate and forecast discharge, how would you distribute your money? So if you rank something highest, you'd say install more gauges. And if you rank it lowest, that's install more gauges is highest for now. And I guess in my head, I was implicitly thinking of the US, but you could answer this for the globe as well. Wow, it's a pretty modeling heavy conference, but okay, there we go. I thought for sure that the community part would be elevated, because as an outsider to this community, I have been very inspired by the sort of person first approach to this community. It's not sort of super heavily focused on the models. I felt very included, and I really appreciate that. So I like the community vibes. There we go. I'm like pumping it up. It's rising in the ranks. This is really interesting to me, and I kind of wanted to ask these questions in part just because it's rare to have sort of 100 physical scientists in a room that you get to ask how they would invest their money. So thanks for doing that. I'll bring it back to these in a second. Okay, so in my experience, working towards some of these things we just looked at, I've found that cleaner data builds a larger community. So there is a lot of data out there. It's overwhelming. But if it's not clean, only the subject experts that have been trained in that can use it. And so you might be excluding like the computer scientists who need novel problems to explore, or you might be excluding the sort of mathematicians who don't know that this is an area that there's plenty of data. I didn't know that you could thumbs up the slides. It's kind of exciting. And when you have a larger community, I think that you can do better science. And that's evidenced by this meeting. I feel like I've seen that a lot today, these interchange between modeling specialists and data scientists and machine learning, et cetera. And then I think when you have a better science, you have a bigger impact. So the talk we just saw, I really liked this sort of emphasis of mapping all the way from flood risk to cost and then thinking through. And that's, of course, going across a bunch of different science is really transdisciplinary. And so for me, what my group focuses on in large part is that cleaner data part. We want to make cleaner data to make larger communities. So how do we do that? Well, I have several projects where I've done this. I have to mute this, otherwise I'll hear my own voice and I will feel terrible about myself briefly. Okay, thank God. Why is it grayed out? Don't gray. Press enter to play video. Huh. There we go. Okay, so I have several projects where we publish some data sets. This is the project that I thought when I published this, it would like change the world. It's called Aquasat. And what Aquasat is for a very long time, people have been going out for federal regulations to rivers and streams and estuaries, and they've been collecting water quality data. And when they're collecting that water quality data, largely that data is sort of disconnected. But in the 2010s, the federal government started to build this thing called the Water Quality Portal. So it's 420 different organizations that collect water quality data, contribute that for their regulatory needs. And in this analysis, we were focused on water quality measurements that have some impact on the color of the water. So we focused on chlorophyll A, that is representative of algae. So if there's more algae, the water is greener. Dissolved organic carbon, which actually doesn't always have color, but the colored component of it can. So you can think of like black water in a swamp. Total suspended sediment and Secchi depth. Secchi depth is just a measure of water clarity. You have a little frisbee, you put it in a lake or a river, and the deeper that you can see it, that's a deeper water clarity. So like 12-meter Secchi depth would be a really clear blue setting. But that data was fundamentally disconnected from another data source that was far less biased and far more comprehensive. And that's remote sensing. So this is Landsat 5 right after it was launched, sort of sampling. When you see a gap in Landsat 5, it's because that day was too cloudy. When you see the river or the lake light up sort of like cyan colored, that's because Landsat actually saw that river on that day. Landsat 5 was lonely because of Landsat 6 exploding. But then Landsat 7 successfully launched and joined it before it had its own scanline error. And now you start to see this really much denser time series of information. So this was sampling in the US every 8 days. Once you include clouds, some parts of the country like Arizona, you really do get information every 8 days, but like if you're in the Pacific Northwest, it's like once every 2 months, sadly. And so then you had Landsat 7, Landsat 5, and Landsat 8 all sort of going. Landsat 8 launched, and then this visualization stops in 2019. And that's sort of where we're at now. We have Landsat 9, and then of course Sentinel have joined these. So there's been eyes in the sky on water quality for a very long time, but for the most of the time, remote sensing of water quality was reserved towards the remote sensing of water quality community, who are largely optical physics-based researchers. I don't understand optical physics. I have an ecology PhD. So what I wanted to do was pair these data sets. So now we have these times when someone was randomly out in the field, they collected a water quality sample, and it happened to be the same day that a Landsat image was taken. And so now we have actual concentration of something we care about, so let's say it's suspended sediment, and the color of that pixel on that day. And so that is what we called a matchup. And so this data set, Aquasat, is now a matchup of more than 600,000 matchups. 400,000 of those are Secchi depth because that's the easiest thing to collect. And then a bunch of them are total suspended sediment. Very few are dissolved organic carbon, and a medium amount are chlorophyll A. And so this is just the matchup data set that we built. We published this paper in 2019, and I genuinely thought, like, man, all these people are going to be doing machine learning of water quality now. It's going to be so cool. I'm going to be cited a million times. Tenure, here we come. But for the most part, that has not entirely happened. And one of the reasons it didn't happen right away is that when you build a data set that's for developing machine learning algorithms, you have to build the same data set for applying those algorithms. It's pointless to have 600,000 matchups if you don't have a way to apply it. So after I finished my postdoc with Tamlin Pavelski, my close friend John Gardner started his postdoc, and what he did was built stacks of imagery over every river. So this paper is called The Color of US Rivers. You can go zoom in anywhere. Or wait, I should probably zoom in where we are. You guys are going to have to help me out. There we go, New Jersey. Yeah, I went to Philadelphia. Yeah, somewhere in here, whatever, the Hudson. So this is basically a data set that any Landsat visible pixel, which Landsat really can't see these rivers very well until they're 60 meters or wider. Now we have a stack of all the images we ever had that are cloud-free, and this is just the raw color. So this is just straight up Landsat spectral information, and we can look at the trends in just the color. So now I built Aquasat, John built River SR, and now you have something where you can develop a machine learning algorithm to predict suspended sediment or something you care about, and then you have an algorithm or a data set over which you can apply that algorithm to get a deep time series of something like sediment concentration, which indeed is what John did. How do I get back into full screen? F? Yes. So John took these data sets, merged them together, and now just recently published a paper in 2023 on the mean suspended sediment concentration for every river for every Landsat image. So from 1985 through 2019, anytime that Landsat saw a river, we know its suspended sediment concentration. And this was a really powerful tool that I think we haven't really even explored the data yet. But what you get to see with this kind of tool is a new way of looking at river sediment data. Normally, we're used to thinking of this as change over time across a single site, so like more of a Eulerian view of the world. But this is, now we have snapshots, and what John did here is just, these are annual averages of sediment concentration for a bunch of famous rivers. And what you see across the entire US, we had a decline in sediment from the 80s through now. And that's not because of dams. Most of the dams in the US were already built during this time period. So we attribute that to land use. And that's something that you wouldn't necessarily have seen, that it's happening across the entirety of the landscape. You might know that it's happening at the outlet or something, but this is sort of a new approach. And this is like what I was hoping for when we built Aquasat. And the way you do this is through some machine learning sort of approaches. And this kind of approach, we were hoping anybody could come in and do the train, test, validate. They have this data set, they could apply it, pull surface reflectance, apply their algorithm. But it turns out, for the most part, it was just my friends who did this, because I was like, hey, friends, this stuff's cool. So if you look at the track of the people who've been using the Aquasat version 1 data, it's basically an entirely internal community. It's basically my friends. I've gotten a lot of feedback from the community, like I get an email 2 to 4 times a week, maybe it'll increase after this meeting, that people find the data set confusing and they find the paper confusing. I was coming from a very local watershed biogeochemistry background, not an optical physics background, so I was pretty ignorant, and I was also pretty arrogant, to be honest. I thought if you just paired these data sets together, it would sort of take off, and the reality was I didn't know enough to make the right decisions to do this the best possible way. So I since then have become aware of a lot of other data sets that I think have done a much better job at this, and one of them is camels. So how many of you know of camels? Less than I thought. That's great. Camels is the catchment attribute in meteorology for large sample studies. So this is a data set that basically took a little bit more than 671 catchments, and harmonized the discharge data and the precip data and all the drivers of what you could possibly think of how precip gets converted to discharge. But they did it in a way that just made this really complex data extremely simple. And it has like lit an absolute fire in the machine learning prediction of discharge estimation. So they accomplished through this data set sort of what I was hoping I would accomplish with Aquasat, and they're cited like 4.5 times more than me, which I think just comes from the fact that they were already sort of deeply embedded in the hydrology community and understood what the community would need better than I did when I was making mine. And camels is a still very inspiring data set. And as such, it's built, now there are camels Great Britain, camels Brazil, camels Australia, camels whatever. So people have been so inspired by this thing, they're making it for every other country in the world. And you put them all together and the camels become a caravan, which is actually the name of the paper, which is great. So after Aquasat and reading about camels, we were lucky enough to get some funding to build another data set that is very much like camels. And this data set is called macrosheds. So when you're doing a physical hydrology budget, how much water is going where, what you need is input water, some information about the landscape, and then output water. That's sort of the basic thing you need. If you want to add in the watershed biogeochemistry component, you need to add input water plus input chemistry, landscape things, output water, output chemistry. So that's what macrosheds is. Macrosheds is focused on harmonizing data across probably the worst possible. These data sets are so different because they're from the LTER, NEON, US Forest Service, Critical Zone Observatory, some individual PIs, which if you're like me, that is hard to make your data talk to each other. And so this is just a data set of more than 160 different watersheds that have information in them. And what you can do if you go to macrosheds.org, don't do it right now because you'll crash our tiny little shiny server, you can add information and directly query watershed biogeochemistry properties of this. This project, we sort of are at the phase of finishing this data set and just starting to explore the science, but I think we did a much better job making this clear and understandable to the community, and the potential value for it, I think, is also pretty clear, because in the history of sort of like watershed science, we've almost always focused on watersheds that are bigger than 10 square kilometers. But in the case of macrosheds, almost all of our watersheds are less than 10 square kilometers. So that pink tail at the end, we're really focused on these really tiny watersheds. And the benefit of that is that when you observe these watersheds, you don't get this hydrologic schmear where like, as you go further and further down a network, the direct landscape control on the hydrology or the biogeochemistry starts to get spread out, and you can't tell if it's the landscape changing or if it's riverine properties. So we feel like we're adding a lot of value. I love these thumbs up. They just really keep me going. And we just started to explore these some of this data that where we're just kind of trying to answer some broad scale watershed biogeochemistry questions that were not answerable before because these data weren't all together. So how and why do watersheds vary in the magnitude, timing, and form of nitrogen exports? Oops, I have to like enter, whatever. How are these changing over time? So we've done a bunch of trend analysis. This is pH. We have silica concentration, and then we also have annual air temp. So we're just starting to get started on that. Oh, I have to get out of there. Okay, so some lessons learned, and then I'll wrap up. Basically, we learned that if you build it, only your friends will come. I think that these data sets are not really like so inviting. They go out, there's so many publications, there's so much data out there, it's really hard to build community around data sets. And so the next approach is that you have to pair code, data, tutorials, outreach, and you repeat that process over and over again to really build a community. I think Camels has done an amazing job with this. And then you need a lot of different on-ramps for a diverse audience if you actually want to diversify. So I get a lot of emails from computer scientists wanting to use this in like their classes as a data set. But it's actually, the original Aquasat was not built for that. But happily, we have funding to build Aquasat V2. So we're developing this with community engagement from the start. So we have external reviewers, 3 reviewers for every parameter, so chlorophyll A or DOC or whatever. We have ridiculous extensive documentation. We have a lot of tutorials and workshops. Maybe I could do a clinic next year. And then we're also trying to build intuition by helping people actually see what the satellite sees. I won't get into that because I took too long. So in the end, what I hope my lab can do is do what this really cool guy, Cosmo Sheldrake, does, which is to take some disparate data sets and value them for their individual contributions, and don't sort of like, definitely give back the value to the community who generated them, but then compose them into some music that'll make it easier and more exciting for people to join a field that would otherwise be somewhat intimidating and difficult to join. So with that, I think I'm done. We can listen to Cosmo for a second because I love the song. The song is called Don Chorus. But what he's doing here is adding some backbone to connect all these different sounds. Okay, thanks.
Thanks so much for the inspiring talk. Do you have any requests or desires for like the agencies maybe that produce data? So you take a lot of data and you make it tidy. Do you have requests for the data that you get for input that would make it easier for you to do what you do?
That's a great question. We work directly, so a lot of this is funded with the USGS, and we work with the data science branch and others, but we're often one layer away from the field crews generating the data. I think one of the things that's really exciting with the next generation water observation system, the NGWAS program, they're installing a lot more water quality sensors, which is this area that we've had the technology for a long time, but the feds have not sort of installed as many water quality sensors as is possible. And so that's been an area where once you have water quality sensors and satellites together, you get to do a lot of much more interesting science that we're really excited to work on. And so I think the biggest one for me is water quality sensors installed in streams and lakes. So buoys, yeah.
Thanks.
I'm like in the acquaintances group. So it took us a long time to pick up on Aquasat, but like I'm happy to say we have a manuscript submitted that uses
yay.
Aquasat. So
Yay! That's great
it's
news.
on Arctic rivers, and we could not have done it without Aquasat being there. So
Yeah, we need to fix that.
When you're cleaning up the data, does information about like missing data or if there's clear biases and you correct that, does that information get passed along so that people can?
So that's one of my original sins in Aquasat. I didn't make back joining to the original data very easy with the way I structured it, which was a screw up. And Aquasat version 2, which we're making now, does exactly that. If any, I didn't want to go through the documentation, but every single decision we make that cuts out data or changes it, we have like very assertive documentation, so you can't miss it. And then also we just strongly encourage back joining to the original. If you have, so water quality portal downloads include like 70 columns, and ours includes like 30, because a lot of them are just filled with NAs. But if you have some really specific thing, like a good example would be sometimes there's suspended sediment concentrations where they sample actually at different particle sizes. And we drop that because it's not, at the scale we're working, it's not useful. But if you wanted to know particle size distribution, you could back join and go grab it. So we're trying to preserve that. It is very difficult. Any of you who've harmonized data, there's just like 1,000 choices you have to make, and documenting them. It's hard to make it like simpler for more people to use it, but then comprehensive. It's just a very difficult exchange.
All right, I think we have to move on.
Yeah, thank you.